Okay, we're back. This is the second video of chapter 10 for Physics 125. So we've talked about the inclined plane. We've talked about the pulley, or I'm sorry, we talked about the inclined plane and the lever so far, the different classes of lever. We've also talked about mechanical advantage and efficiency. All that was in the first video. And now we're going to talk about the four remaining types of simple machines, and then we'll be done. So to start this time, I would like you to watch the Eureka wheel and screw video. Again, it's just 5 minutes. And it covers both the wheel and axle and the screw, and then we're going to go through and talk about those on the subsequent slides. So wheel and axles, as it described in the video, as it describes it here on the slide, they're basically levers, but they just go all the way around in a circle, right? So we think about a classic example like this one, right? You'd have a handle, and the handle goes around, and that causes the axle to go around, and the axle is of shorter radius than the handle. So the handle is kind of the wheel part with a big radius, and the axle's the drum here is the axle part with a shorter radius. And so we are able to crank something up that would weigh more than we would have to put our force into this handle because the handle is longer. The steering wheel is a more obvious example because you can see the wheel shape of the wheel part, the pedals, and the sprockets on a bicycle. So on this part of the bicycle, it is an effective wheel and axle as we would think of it, because the pedals radius is greater than the sprocket radius. The back wheel is another story, which we can talk about at another time. But again, it can be used for lifting, but obviously on a bike, it's not used for lifting. A steering wheel is not used for lifting. It's used for turning or for guiding. So it's all about the radius of the wheel and the radius of the axle. Those are the two distances we're going to be comparing. And again, similar to the lever, that's because the distance you actually travel is directly proportional to those radiuses and can be used in that way. So here's a numerical example for the wheel and axle, right? Somebody turning this handle to raise a bucket. If the axle has a radius of 12 centimeters and the wheel has a radius of 62 centimeters, what force must be applied to the rim of the wheel in order to lift a weight of 975 newtons? Now that 975 newtons is hanging on a rope that's wrapping around the axle. So that's just a little extra understanding of what's going on in the problem. And then also, what is the mechanical advantage of this simple machine? So again, we take a look at FD for effort and FD for resistance. Again, those are going to be set equal to one another. The wheel is where the person puts in the effort most of the time. So we don't know the force on the wheel, right? That's the question. What force will be applied to the rim of the wheel? So we don't know the human effort force, but we do know that the wheel has a radius of 62 centimeters. The axle has a radius of 12 centimeters, and that the weight hanging on the axle is 975 newtons. So we've got three of our four numbers. Multiply those two together, divided by the 62. So we got 11,700 Newton centimeters divided by 62 centimeters. Again, as I noted in the previous video, it doesn't matter really whether it's centimeters or meters. What matters is that we are consistent between the two sides of the equation, because now these centimeters are going to drop out and our human effort part is going to be in newtons, which is corresponding to the units of force we were using on the other object. So we discover that we have to use a significantly smaller force to lift it, and that's the idea of a simple machine, right? But how much smaller? What is the mechanical advantage? Again, mechanical advantage is the resistance force divided by the effort force. How much weight did we lift divided by how much force did we put in? We lifted 975, we put in 189, so that's 5.2 times more lifted than we put in. So that is the mechanical advantage. The mechanical advantage that this machine gave us was to multiply our force by 5.2. So a second example, the diameter of a wheel and axle is 10 centimeters. If the force of 475 newtons is raised by applying a force of 142 newtons, find the diameter of the axle. So you'll notice in this problem, it was both about radius. In this problem, it's both about diameter. Again, as long as we are consistent, we can use either the radius or the diameter or the circumference for that matter in here as the appropriate D in our work equation, as long as we are consistent. So here was a little bit different. They gave us the diameter of the wheel, which is the effort part. They gave us the force for the wheel, which is the human effort part, all right? They raised by applying. So we applied 142 newtons, so that would go with the wheel. And then we lifted 475 newtons. That would be the weight that we are lifting. So, and I wrote this wrong. All right, let's try that again. So the problem is unchanged, but now the math is correct. So this is the diameter of the wheel that goes with the person's force being applied to the wheel. 142 newtons is the person's force. 10 centimeters is the diameter of the person's wheel. 475 is the weight lifted by the axle, and then we don't know the diameter of the axle. So we multiply those together, we get 1420, we divide it by the 475, and we end up with a diameter of the axle of 2.99 centimeters. So that just demonstrates how important it is to make sure that you have the right force connected with the right distance going with that force. Again, very often you're going to be given three numbers, and they're going to fall pretty easily into either the F or the D category, but if you put the wrong distance with the wrong force, then when you divide out, you're going to end up with the wrong answer. So very important, read the problem, see what the context clues tell you, right? If we're applying a force, that's the human. If it's the diameter of the wheel, that's the human effort part. If something's being raised, that's usually the resistance part. And the axle is the resistance in the wheel problem. So that's wheel and axle. Now we're going to move on to screw. In many ways, the screw is the hardest of the simple machines. It's a very common one that we're familiar with, but mathematically especially, it is more challenging than some of the other simple machines, just because there's an extra level of math and thinking that you have to do. Conceptually, the screw is not that complicated, right? It's the inclined plane. It's that ramp idea, but it's being wrapped around in a circle, right? So as we turn this bolt, we can see this sloping line that goes around and around and around the bolt. And so as we turn the bolt goes into the ground, but of course we turn it a great distance and it only goes into the surface a small amount. And that small amount is referred to as the pitch. The pitch is the distance between two threads at the same point on the circle. And so when you make one full complete rotation of your wrench or whatever you're using to turn your bolt or your screw, it will have gone in a vertical distance of the pitch. And oftentimes we'll be told things like threads per inch or threads per centimeter. How many threads we get in a certain unit of distance, and so the pitch is going to be 1 divided by that. In units of whatever the distance was that they gave you. So obviously inches are common. A very common pitch is 8 threads to the inch. So then the 8 threads per inch will give us a pitch of 1/8, 1 divided by 8 or 0.125. Very common pitch. So the idea here is that we're going to turn it all the way around in a circle. And so that's going to be a full circle is 2 pi r, the full circumference. So whatever they tell you the length of the handle or whatever this radius is, 2 pi times that radius will be the total large distance. We turn it around, and in that process, we only go in the pitch. So ultimately, these two expressions don't change, right? The ratio of the forces is the mechanical advantage. The ratio of the distances is the ideal mechanical advantage. Again, if there's no friction, then we're assuming these two to be equal. But what's different here is what is the effort distance? The effort distance, I am turning that wrench all the way around in a circle. So that's the effort, the distance I'm applying my effort. So that's 2 pi r. And the resistance is how far it went into the board. So 2 pi r over pitch is that IMA, which can be equal to the MA in the absence of friction. So here's a bunch of examples of additional screw types. I showed you that jack screw at the beginning. the jack that you use that they sell you and put in your car for you to change the spare tire is also a type of screw like this. These screws are not bringing two things together the way that one does to scissor lift up your vehicle. But a wood screw, right? We're familiar with trying to screw these into wood or something like that. The auger bit would be is screw shaped to pull out the shavings and to help make the hole. And then of course a snowblower has an auger shape to pick up the snow and send it to the part of the snowblower that's going to blow it out. So here's an example using that jack design. Um, Again, very heavy car is raised using a jack screw that has 8 threads to the inch and a handle that's 15 inches long. Remember, 15 inches is just a little over a foot, right? So that would come with your jack, and you'd hook it into that little eye hook there, and you would use it to rotate the jack. So what effort force must be applied to lift this car? And then what is the mechanical advantage of this jack? So again, we have the same basic expression, but I've just added to that basic expression the definitions of our distances, since they're a little different for our screw. So it's still effort force, effort distance, resistance force, resistance distance, but now our effort distance is 2 pi r, and our resistance distance is the pitch of the screw. So they told us the weight of the car. That's what we're lifting. That would be the resistance force. And they told us the length of the handle. That would be our radius. So we have 2 pi times that radius in inches, and we don't know what the human force is going to be yet. And then on the other side, we know the weight of the car, very large, right? 3,500 pounds or 3,650 pounds. And the pitch is just 1/8 of an inch, 1/8, 1 divided by 8.125. But I put it in there as the fraction for now. So this is all a number, and this is all a number except for FE. So we can now proceed with our favorite game in town, which is algebra, of course. So 3,650 divided by 8 is 457, and 2 times pi, right? Pi is a little more than 3, so 6 times 15 is going to be a little more than 90. So 457 divided by 94, the human effort force. How much force do you have to put on that jack handle in order to turn it and lift your almost 4,000 pound car? The answer is a little less than 5 pounds. Little less than 5 pounds. So this is the power, incredible power of simple machines, that I can lift almost 4,000 pounds with a force of 5 pounds. If I do it right, if I have the right device for this functionality. So how much is that multiplying my force? What is the big mechanical advantage that I'm getting? Again, what am I lifting divided by how much force am I using to lift it? So 3,650 divided by 4.9, I'm getting a mechanical advantage of 745. So my force is being multiplied by 745 times. Again, the incredible, incredible power of simple machines in our everyday lives. Who needs an engine? We don't need an engine. We have simple machines. So here's another screw example. Again, these are more complicated. We're doing a couple of these. A wood screw has a pitch of 0.125 inches. Again, here they just directly told us the pitch. This is, again, 8 threads to the inch. It's the same thing. It's advanced into the wood using a screwdriver whose hand is 1.5 inches in diameter. What is the mechanical advantage of the screw? What is the resistance force of the wood if 15 pounds of force are needed to turn the screwdriver? So they kind of asked us here in the opposite order. First, they asked us for the mechanical advantage, and they gave us both the distances. So we can find the mechanical advantage by finding the ideal mechanical advantage by finding the ratio of the distances. But of course, we can't just use the numbers they gave us in the problem, right? Our distances are special in screw problems. It's the diameter times pi, right? 2 times the radius, 2r, right? The radius is the distance to the center of the circle. Where do I got some room to draw a circle? So the radius is the distance to the center of the circle. The diameter is the distance all the way across the circle. So 2 radiuses would be equal to the diameter. So instead of writing 2 pi r, we're just writing pi times d, or d times pi, again, commutative property multiplication. So this was given as the diameter of our screwdriver. So 1.5 pi is the human effort distance, and then 0.125 was given as the pitch. So you divide those two, you find out that our mechanical advantage is 37.7. Not quite as good as the jack screw. We're not lifting a car this time, but we are still greatly multiplying our force to put in the screw. So then they want to know how much is the wood resisting if it took us 15 pounds of force to turn the screwdriver, which, again, if you think about turning a jack with 5 pounds, 15 pounds is quite a bit of force to be putting on a screwdriver. But we can go back to our same approach, right? Effort, force, effort, distance, resistance, force, resistance, distance, with our special definitions for this problem. And the 15 pounds we're putting in times the pi d distance that we're going. And then over here, what's our resistance times that 1/8 of an inch distance. And we find out that the wood is resisting quite a lot, right? But we are able to drive that screw in, and effectively that is the, that's labeled incorrectly. And now it's not labeled incorrectly. So that is the resistance the wood is giving. And if we're driving our wood screw into 2 pieces of wood, that is effectively the force that wood screw will hold those pieces of wood together with. Again, it's all these little ridges along the screw. Each one of them is pushing the wood down, or pushing the wood up if the 2 pieces of wood are trying to come apart. And this is why screws are so effective at holding wood together in the direction that the screw goes, right? If you drive a nail in, it'll be very good at holding the wood if the wood tries to shift perpendicular to the nail, but it's not very good at holding the wood in the direction the nail was driven. Screws are incredibly good at holding it. If you've ever tried to rip a screw out with a hammer, this number becomes very real to you, because it is not easy, even with using the lever of the back of the hammer. It's not easy to tear that screw out. Many times the wood will fail around the screw before the screw itself will come out. And if you start putting several screws in, all right, how many things are attached by a single screw? Right, 2 screws, 3 screws, 4 screws. Take 4 screws, multiply it by that number. That object's being held in with an incredible amount of force. But going back to this mechanical advantage for a moment, right? This is how much our force is being multiplied. That's what mechanical advantage really means. So we could have done the second part of this problem in a different, considerably simpler way. Once we'd done the first part, we'd found the mechanical advantage was 37. And then we're told, well, you're going to use 15 pounds of force. What is the resistance force going to be? Well, my 15 pounds is getting multiplied by my mechanical advantage. So effort force times the mechanical advantage equals my resistance force. And that's a very simple, if you just rearrange this equation, right? If we take the Fe to the other side, multiply both sides by Fe, I've got Fe times mechanical advantage equals Fr. So when you do that, 15 times 37.7, once again, you get 566 pounds. You get the same answer as we would expect. So 2 different ways to do that problem. So now we've covered wheel and axles, and we've covered screws. Again, rewatch this part if these problems are challenging. If you're having a problem with these in the homework for chapter 10, come back and rewatch the video. I do these example problems to help you understand and be able to rewatch and see them again. So now we are on to the last Eureka video, the second to last simple machine. This is the, So again, go to YouTube, watch the Eureka Pulleys video. Again, there's a link in the description. This is the last one. Again, very powerful video to help you understand how pulleys work before we talk about them. So you watched the video. I'm going to explain it to you again. Again, repetition is very powerful, right? Especially when you're learning a new concept. Here we have the very same expression we've seen a bunch of times, right? Resistance force, resistance distance multiplied together equals effort force, effort distance multiplied together. Same principle we come back to over and over for all these simple machines. For a pulley, just to talk conceptually about what's going on with a pulley, right? We have a string and the string is attached somewhere and it's running over a couple of wheels. And when we pull on the string, all of the string that's attached is going to pull. And when we have the string doubled or tripled or quadrupled over, when I pull with some force, then I have multiple strings holding up the weight of the object. And so they split the weight across themselves, and therefore the force I have to put forth is less than the overall weight of the object. Now, I would like to point out to you that this string and all the strings are not tied directly to the weight. If you throw the rope over the pulley and you try to tie directly to the weight, then every foot I pull the string, the object has to go up a foot. You're not going to get any mechanical advantage, okay? But if you run the string around and you tie it to the pulley, or if you ran it through a second pulley and then you tied it to this pulley, not to the object, but to the pulley supporting the object, then you are able to get the advantage that you want to see. So here in this case, there's just two strings supporting the object. So when I pull a foot, each string shortens by half a foot. The object only goes up a half a foot. I have to pull a foot. But in compensation for me having to pull further, I have to pull with less force. And this effort force is only half of the weight of the object. So again, pulleys are extremely visual in their nature. So we're going to end up looking at a lot of pictures here. This is that simple case that I talked about, just throwing the string over the pulley. It is helpful for us in the sense that it changes the direction. So I can pull down here and that will cause my object to go up. This is one fixed pulley because the pulley is fixed to the ceiling. This is called one movable pulley because the pulley is actually going to move as I pull the rope. The rope is tied to the ceiling and then comes around the pulley, and then I pull upward on the other side of the rope. So there's two ropes supporting the object. So they're going to split the weight of the object between the two of them, and therefore the tension in the rope and the effort I have to put forth is only 1 Newton to move a 2 Newton object. And then you can keep going here. Now we have a movable and a fixed. You'll notice in this arrangement, there's still only 2 ropes lifting the object. The advantage here is that I get to pull down. So here we get a multiplication of the force. Here we get a change of direction. Here we get a multiplication of the force and a change in the direction. And then you can get into these more complicated situations, right? And what you ultimately end up discovering is that if you count the number of strands that support the object you're lifting, that will be your mechanical advantage. So you got to be careful though. Only count the strands that are supporting the object. Okay. Here, if we extended this string down, you might be tempted to count it, but it is not directly supporting the object, right? It goes over a pulley before it supports the object. But there's 1, 2, 3, 4, 5 strands directly supporting the object, so the object's weight gets divided by the number of strands. Now they keep putting a heavier weight on here so that we always pull with 1 Newton of force. But that's essentially the way the world works, right? We as humans are limited in the force we can apply. So if we need to lift a heavier and heavier object, we have to create a more and more complex pulley arrangement to make this work. And you don't usually use these pulleys in real life because they take up so much space, this larger, medium, smaller arrangement. We put all the pulleys next to each other in what we would call a block and tackle arrangement, but that's harder for us to see. So they like these on the slide when we're trying to understand. So here's a couple of examples. What's the mechanical advantage in each picture? You can pause the video and pull out a piece of paper and write down your answers for 1, 2, 3, and 4, and then I'll talk through them. Here I've only got 1 rope supporting the weight, and so the tension is going to be the same as the weight of the object. So the mechanical advantage of this is 1, but we do get to change direction. But mechanical advantage is 1. Here I've got 2 ropes, so that gives me a mechanical advantage of 2. Here it's also 2 ropes, still a mechanical advantage of 2. And here it's 1, 2, 3, 4 ropes, so mechanical advantage of 4. More complicated examples. Pause the video for a moment. Figure out the mechanical advantage. One, two, three, 4, 5, 6, 7. It's not 7, right? The 7th one is not actually supporting the weight. It's where I'm pulling. So it's the other 6. 6. Mechanical advantage of number 1 is 6. Mechanical advantage of number 2. So here's the block and tackle arrangement that I was describing. And you see it's a little harder to count the ropes in this arrangement. I come down here where I don't think there's any on top of each other. 1, 2, 3, 4. So mechanical advantage of this one would be 4. So again, pulleys, you look at them and you carefully count the strands, and that's how you figure out your mechanical advantage. And then as we discussed with that final screw problem, if you have the mechanical advantage, then you can figure out the relationship between F and W, right? It's simply F, which in this case, F would be the human effort force. Human effort force times the mechanical advantage equals the resistance force, which would be, excuse me, the weight that we are lifting. Okay, the wedge. This is the last one, and we're not going to do any math with the wedge. We just are rarely asked to do that in an introductory physics class, and by now you've seen 5 other simple machines, and therefore the math should be clear to you as to what you would be doing if you were doing the math of a wedge. It's just not something that we do very often. But a wedge is simply the inclined plane turned on its side, right? So here we can see that same ramp type design, okay? But we don't usually use wedges sideways. We usually use them up and down. So if you turn that thing 90 degrees and you apply your force to the top, right, with a sledgehammer or with just think of your knife when you're cutting steak or cutting anything at the table is a wedge, and you apply the force downward on your knife, and the point of your knife is able to cut through the food because of this shape, and it separates the food to either side as the wedge goes in. The longer the wedge and the narrower the wedge, the higher your ideal mechanical advantage is, the less force that's necessary. So again, that's simply the length divided by, so if L gets bigger, we're going to get more. If the T gets smaller, if we divide by a smaller number, it's going to get bigger as well. That's the principle. You don't always see long, very narrow wedges when you're splitting wood, because then you get the situation where you drive the wedge all the way into the wood, and yeah, it went into the wood, but the wood hasn't split apart. So it's this way in a lot of simple machines. We try to make them as efficient as we need them to be, but no more, right? Because we are paying a price, and we're paying a price in terms of the distance we have to move it. So yeah, you could design a jack to lift your car that only required a quarter of a pound of force, but you would have to be turning it so much further to do that. You know, it's no accident that that number came out to be about 5 pounds when we did the screw problem, because that's considered to be a normal force that a human could apply consistently for a long period of time. So they got it down to 5 pounds, but not much below 5, because you don't want to have to be turning it a million circles. That would be frustrating and irritating. So this is, again, how the wedge works. We apply the force on one end. The force is then in turn driven in the other directions, and the wedge will go down and penetrate into the object. A fatter wedge will split the wood quicker, but it will require more force to be applied. So try to get that balance. So the very last thing we're going to talk about is something called compound machines. We spent the whole chapter talking about simple machines, and again, simple machines are human powered. A compound machine would still be human powered, but a compound machine is when you string a couple of simple machines together. Maybe 2, maybe 3, maybe more than 2 or 3. There are possibilities, and really you can think, for example, of that jack that we use to jack up the car. You could think of that as a compound machine, because yes, there's a screw, but then there's also a handle that sort of makes it a wheel and axle type arrangement. But all that is built into the way we do the screw part. But here we have a wheelbarrow full of dirt, and we're using the fact that it's a wheelbarrow, so it's a lever, but we're also using the fact that it's a wheel. But this wheel we're going to be using a little differently, right? When we think of a steering wheel, we put our force in on the wheel part, and we get the lifting ability out of the axle part. But when you pick up the handles of a wheelbarrow and you push it forward, you're putting your force on the axle, and you're getting the force out on the wheel. And so I made reference to the bicycle example earlier. And we talked about the sprocket and the pedals, and how the pedals have a greater radius here than the sprocket wheel does. But if you go to the back of the bike, you've got this little sprocket wheel, and you've got a big wheel that the sprocket wheel is turning via the chain. Wow, I draw beautiful bikes, don't I? So here we've got a little radius where we're putting in the force at a little radius, and the wheel has a large radius. And as I mentioned with the baseball bat, when we do a machine backwards like this, it's because we want something different, right? We want to be able to turn our pedals once and have this little sprocket wheel go around maybe a couple of times, right? Because this circle is, no, we're attached by a chain, right? It's pulleys like we learned last time. So if I go around once, and then this wheel is going to go around close to once, because these are pretty close in size. But when this sprocket wheel goes around once, the big wheel is going to go around once. So my feet make a little circle, right? 2 pi little r, and then the big wheel makes a circle, but the big wheel has a big R. So I get to turn my feet around maybe a foot and a half diameter, or a foot and a half circumference circle, and then my big wheel goes down the road a circumference of, say, 5 feet. So my feet only have to go a foot and a half, and my whole bicycle goes 5 feet. And so what I'm trying to say here is we are multiplying our distance instead of multiplying our force. And that's the idea. And that's what's going on here with the wheelbarrow as well. When we apply our force to the axle and the wheel rolls out, then our force is being actually divided, but our distance is being multiplied, which is helpful to us. So let me take these numbers from the picture and stick them into this compound mechanical advantage. Because again, the principle is that we just multiply the smaller mechanical advantages together, and that will tell us the overall mechanical advantage. It's not behaving. Okay, so the mechanical advantage of the wheel. So again, we are putting our effort in at the axle. So we've got to put our effort in with the small distance and divide it by the radius of the wheel, the big distance. So this is the wrong way, and we're going to get a mechanical advantage of less than 1. So we're actually dividing our force effectively the way we use this wheel. But the lever arm of the wheelbarrow, we get a above 1 mechanical advantage, right? So we're lifting at this large distance from the fulcrum, 1.87, and the dirt is being lifted at this smaller distance. So 1.87 divided by 0.568, and so we get a little bit over 3. So those are the 2 individual mechanical advantages. We put them together. The wheel 1 times the lever arm 1 gives us the compound 1, 0.283 times 3.29. We get an overall mechanical advantage that's a little less than 1. Again, the advantage here, amongst other things, is we get a push forward, and the wheel rolls it out for us, which is nice. That's a lot less friction. And that's basically how the compound machine is going to work. So that's simple machines. Hopefully that made sense to you. Again, watch the video again if you need to. It's kind of the same math over and over again when we're solving for the force or the distance. And then we have our mechanical advantage equation and our efficiency equation. If you have questions, email me, text me, let me know. This is chapter 10, the end of chapter 10. We just have one more chapter to go.